My name is Anup and I am here to give a demonstration of the impact of quantization of sensor values in energy harvesting networks. The problem statement is whenever the sensor parameter is being monitored, there is a scope for decreasing the input energy. So when the input energy shows a decreasing trend, it is necessary to implement some energy conservation algorithms. There are several approaches that exist, such as lowering the input voltages or varying the sampling frequency, duty cycling, etc. One possible approach is to monitor a range of parameter values rather than a particular value. This helps in studying how the sensor parameter is varying with respect to time, and this trend that the sensor parameter takes can be used to predict what the future values will be. Based on that, I will be deciding what the resolution as well as sampling frequency that we can decide. So here this shows an implementation of a pictorial representation of the algorithm that is being implemented. When the input energy is fully available, then irrespective of the sensor parameter being monitored, I will do a highest resolution of sensing. When the input energy is at the critical level, then I will be implementing an algorithm wherein the resolution as well as the sampling frequency will be varied dynamically. In order to predict what the future sensor parameter values will be, I have implemented a statistical modeling procedure called as autoregressive modeling. The autoregressive modeling is basically I will be constructing a master data set. I will be trying to model a pattern in the master data set, and I will be getting an equation. The model equation is as shown here. The quality of the model is decided by the sum of squared errors that we derive from the model. The sum of squared errors is 0.0174. Here a snippet of the GUI that I have implemented is being depicted here. The input energy is varies based on Bernoulli injection probability. The maximum input energy is obtained when the probability value is 1, and minimum input energy is obtained when the probability value is 0.2. Through this implementation, I have been able to observe that there is 50% of energy savings that is obtained. This is the setup of my demonstration, wherein I have a solar simulator that where the harvested input energy is varied based on the principle of Bernoulli injection of probabilities. The input energy is injected into the source node or sensor node. At the sensor node, the algorithm is implemented based on the input energy that it derives and transmits the data. At the base station, I have a GUI. Which depicts the status of the sensor node. The GUI is grid powered. So at the sensor node, now I will be varying the temperature. As the temperature is being varied, you can see the green line here indicates the predicted value, the algorithm that is being implemented, while the red line here indicates the actual value.